There we go. Okay. So we got streaming. The audio is good. Yesterday, my wireless mic ran out of battery in one of my classes, so half of the class was going to be a silent movie. All right. So what we'll do today is we're going over a practice exam. So the next Thursday, you guys will have your second exam. So make sure you put it on your calendar. Hmm? Next Wednesday, sorry, yes. So next Wednesday we'll have our second exam for this class, which is another 20% of your grade. Um, I think in the first exam, the class in general did really well. So that's good, okay? Keep up the good work. All right, so what we'll do is we're going over the last two questions of one first exam because floating point was part of the first exam in the semester of last fall, okay, but it is not in our first exam, so that's why we'll have floating point numbers in our second exam. Is that okay? All right. So these are the questions in that particular exam. I'm going to zoom in so you can see a little bit better. There we go. All right, so question number 6 out of 7 is a fairly typical way to ask questions like this kind. So I give you a hexadecimal number, and I want you to step by step tell me what is the value represented when you interpret the bit pattern as a double precision floating point number. Okay? All right. So I'm pretty sure some of you, do not quite remember, floating point numbers. Okay? So that means you're going to have to study that, and also make sure that you bring along some material with you. Okay? Either handwritten or printed, so that you don't have to remember, exactly how many bits are allocated to this, how many bits are allocated to that, because it's still open book and open notes. All right. So assuming that you do have that little piece of paper to help you, remember, oh, okay, float a double, floating point number, double precision floating point number is, chopped up this way. So the first thing you need to do is what? You're looking at a hexadecimal representation here. So what would be the first thing to do? Translate it into binary. Very good. Okay, so that's what we'll do, is to turn this into a binary pattern. Now, you don't have to waste your time to write the zeros, okay? Because this has really a whole lot of zeros, like 8 of them. So just write a few, and a dot, a dot, and then the last one being a zero. I'm totally okay with interpreting that as, okay, this is a whole bunch of zeros. So what we'll do is we'll start the conversion, okay? And let me download this journal. Okay, so we'll go ahead and download this file and open it in Zernal. The best thing about opening this up in Zernal is not that it is just local, but also because I can mark it up. I can just write down the answer here interactively, and I can do things that I cannot easily do using a text editor. That's a beat pattern. Is it a feedback? Okay. I know it's not coming from my recording because it is held as private, so it's a feedback from something else, and it's not from here because if it's from here, you guys will all be covering your ears. You want to try that? I suppose when you guys are starting to get kind of like sleepy and whatnot, I'll try that. All right, so we look at this one, and the first thing we do is we convert it into a binary bit pattern. So once again, you don't have to give me every single digit, especially the whole bunch of zeros on the right hand side. So we convert it into 4 is 0, 1, 0, 0. Okay, let me choose a smaller not as thick, okay? And then we have 0, 0, 0, 0 as the 0 in hexadecimal. 6 is 0, 1, 1, 0. And then the A is 1, 0, 1, 0. Then we have just a whole bunch of zeros after that, okay? So how do you know how to do this conversion? Yeah, how do you convert from hexadecimal digit into groups of 4 bits? You can print out the table, okay? You can make your own table, okay? Or you can just have it memorized, okay? It's up to you. So, I'm assuming that you will know how to do this conversion. In other words, I will not answer questions about, oh, how do we convert this into a binary bit pattern? It will be up to you to decide, how to do it in the exam. Are we good? Okay. So you might want to jot down some notes, okay, to remind yourself, what you want to bring with you, on next Wednesday to help you out in the exam. All right. So now we have this broken out. Now I can just graphically do it, and so can you. Okay. You can just say this is the sign bit, and then we take a look at the next 11 bits, which is from here to here. Okay. This is our E. And then the rest are our mantissa, okay? So we'll just say this is the mantissa, or M, okay? Now the question is, now this step is worth a little bit of points too, because this shows me that whoever is drawing this picture understands that there are 3 parts to a double precision floating point number, and exactly where each part is in the 64 bits. So this is worth some points already. Okay. So given this picture, then we have to find out, okay, what does the sign mean? Okay, the sign bit is a 0, so that means it is non-negative. Okay, so we just say that, okay, this implies the value being represented is non-negative. All right. Now the E is a little bit trickier because the E is a biased exponent. So that means, okay, we take the E here. The first thing you want to do is to convert this into a base 10 representation. So I won't give you something that is really, really hard to convert into base 10 by hand. This can be converted into base 10 pretty easily because there's a whole bunch of zeros. You just have to figure out where the ones are, what powers of 2 are corresponding to the ones. So we got 1, 2, 1, 4, and this is 1024. Okay. So now we write this down in base 10, and then we just say that E is 1024 in base 10 plus 4 plus 2, and that will give us what? 1030. Okay, but E2 is actually biased. It's biased by not 1024, it's biased by 1023, okay? So we have to take E and subtract 1023 from it, and that would give us what? 7? Yes? Okay. All right, so what is left is the mantissa. So what do we do with the mantissa? The mantissa means this is the fractional part of the mantissa. So that means the actual mantissa in base 2 is 1.1010 in base 2. Because the rest are all 2, so I don't have to kind of copy the rest. Are we doing okay so far with this? But 1.101 in base 2 is not exactly an easy number to work with because it's in base 2. So we want to convert that into base 10, or at least into some kind of a fraction, okay? Fraction is actually easier to deal with in this case. So we'll say this is 1 plus 1/2 because the 0.1 of -1. And then we also have an 8th here because the 0.01 in base 2 is 2 to the power of -3. Is that okay? Is that part, okay? All right. So once you have this, you can just kind of do the addition. So we basically have 1 5/8 in here. You can either write it out as a mixed fraction like this, or you can write this out as a, just a fraction, but not mixed. So that means we have 13 divided by 8 here. So now, what is the value being represented? The value being represented is going to be 13 divided by 8, which is our mantissa, times 2 to the power of e2, which is 7. Okay, you can simplify a whole bunch of stuff here. You can cancel out this 8 because that's 2 to the power of 3. So that would take out 3 here. So we have 2 to the power of 4 left. So now we have 13 times 16. And it'll just tell me what is the product of 13 times 16. Is that okay? Are we doing okay? All right. Shall we move on? Okay. So if you're looking at this and if you think that you're not quite getting, why we have this extra 1 here, or why we are subtracting 1023 here, then you might want to review the material, okay? Because the whole idea of the practice test is kind of to help you identify what things you may not be very familiar with, and what you can focus on when you study for the actual exam. Yes, go ahead.
Why is it 2 to the 4 at the very end?
Huh? 2 to the power 4, because originally this is 2 to the power of 7, right? This is 2 to the power of negative 3. 7 plus negative 3 is 4. You don't have to simplify it this way. I mean, just use whatever means to simplify it. If you want to multiply this out and say 2 to the power of 7 is 1,128, then you can just say, okay, 128 divided by 8 is 16. Okay, so there are many ways to do it. Calculator can help you with this. Okay, the only thing you want to be careful when you're dealing with using a calculator is you have to be familiar with the power function, because you have to make sure that you enter the base first and then the exponent, before in order to use the power function. It depends on your calculator, so make sure that you read the manual. Okay. All right. So, any other questions regarding number 6? Any other questions? All right. So after number 6, we have number 7, which is the reversal of the whole thing. So in one case, I give you the binary representation of a double precision floating point number. This one is exactly the opposite. I tell you what value I want to represent, which is just 60 in base 10. Now, how do you know this is just 60 and not 60 in hexadecimal?
It's a value.
I could use any base as a value.
But there's no subscript, so it's the same base.
There's no subscript, there's no 0x as a prefix. So without any special notation, you can assume it is base 10. Okay? Now, I could easily tell you this is a hexadecimal number, but then I will have to use a notation, either having a subscript of 16 or a 0x as a prefix, because that is the C notation of a 16 number. Is that okay? Now, it is a value of 60, just to see whether you guys can do the base conversion in your head really fast. If I want to express the value of 60 in base 16, what would it look like in base 16? It will be 3. It won't be a B, because a B is a prime number. It's an odd number. It will be 3. 3 is right. So far, so good. What is 12? Exactly. What is 12 in base 16? C. That's it. That's it. So 3C in hexadecimal would represent exactly the same value. Okay? All right? But I'm not going to make it tricky. In other words, I'm not going to say, okay, this is, the number in base 7, and then you have to convert it into base 10 first. So I'm not going to do anything that tricky. All right. Now, if I do give you the number in base 16, trust me, that's actually an extra help, with questions like this. And I'll explain that later, okay? But this is in base 10. All right, so how do we convert 60 in base 10 into the double precision floating point number format? What do you think? Remember, you wrote a program to do this, okay? So, but this is a lot easier to do compared to the example that you had to deal with when you write your program. So what would be the first step to do when you say, I want to convert 60 as a value into a double precision floating point number? Say that one more time. Start dividing by 2 to get the exponent. Okay, that will work, but I can use a side effect to do that. Okay, I will first convert 60 into just a base 2 representation first. Seems to make sense because in a double precision floating point number, the mantissa is in base 2 and the power is also in base 2. So it seems to make sense that I want to convert whatever value I need to convert into base 2 first. Okay? So how do we convert 60 into base 2? Remember what we said a little bit earlier? 60 is actually 3C in hexadecimal. Yes? If I gave you 3C in hexadecimal, I'm helping you with this process already, because converting a base 16 number into base 2 is a snap. Converting a base 10 number into base 2 is kind of like, yeah, we can do it, but it's kind of cumbersome. Okay? So if I already give you, that this is 3C in hexadecimal, that's easy, because 3C is 0, 0, 1, 1, 3, that's 3, and then C itself is 1, 1, 0, 0. I'm done. We have, the binary representation. Now, if I start with 60, then I have to do the actual conversion and find out that, oh, there's 132 in 60. What is left? We got, 28 left, right? So within the 28, we have 116. And then we subtract the 16 from, the 28? You got 12. And then in the 12, we have 8. You subtract the 8, you have a 4 left, and then you have a 4. Okay, that is actually longer than looking up a table in hexadecimal digit conversion to groups of 4 bits. Is that okay? Yes. So if I give you the same value and I say this is 60, but it is also known as this in hexadecimal, blah blah blah, you know which one you want to use as to start the process. Okay. So how is this going to help me? Well, so we look at this as a base 2 number, and then we say, okay, it's 111100 in this case in base 2. But that is the same thing as 11110.0 in base 2 times 2 to the power of 1. Would you guys buy that? I just put an implicit decimal point or binary point in this case. I move it to the left. But what is the effect of shifting the binary point to the left when we're dealing with a base 2 number? It's divided by 2. But I don't want to change the value, right? So if I don't want to change the value, if shifting the binary point to the left is dividing it by 2, I can make it up by multiplying this part with 2 to the power of 1, which is just 2, right? Okay. But there's a reason why I use 2 to the power of 1 instead of just 2. Because now I can say it's 1111.00 in base 2 times 2 to the power of 2. And you know where this is going, right? Okay. So is it okay for me to skip like 3 steps? Yes? Okay. So now I can rewrite this as 1.111 in base 2 times 2 to the power of what? I have just shifted it 3 more times. 5. Okay, cool. All right. So at this point, I claim that I know all of the pieces already. I just have to kind of work it into the double precision floating point number format. So we know the sign bit. Okay, sign bit is easy to work with. The sign bit is a 0 because the value is non-negative. Okay, so that's the easy one. What about E? Well, we know the relationship between E2 and E. We know that E2, which is the actual exponent in base 2, is E minus 1023. So in this case, we need to reverse it, right? So we know what E2 is. E2 is just this 5 here. So we have to add 1023 as a bias to it. So that means we have, okay, let me just circle this and say this is E2. So now we have 5 plus 1023, which is 1028, okay, which is 1024 plus 4, okay. Now, why do you think I rewrote 1028 as 1024 plus 4? To convert into base 2, okay. So that means E, after all of this, would be 1 followed by almost 10 zeros, but it also has a 100 at the end. So I have to do the counting carefully this time because we have a 100, which is the 4, and then everything in between are zeros. So there are 11 digits to begin with, and this is already 4, which means I only have 7 zeros to fill in. Okay, so we have 1, 2, 3, 4, 5, 6, 7. There we go. And also making sure this is base 2. Is that okay? Does everybody understand the relationship between E and E2 and how we kind of convert between those two? Hopefully. Okay. All right, so let me just double check and count the number of digits because there should be 11 digits here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's see, we are good. I think there are 11. Yep. All right, so what is left? What is left is the fractional mantissa. In other words, what I do represent in a double precision floating point number is not 1.111. The 1 point is implicit. Only the 111 is needed in the double precision floating point number. So the mantissa that I need to store, which is the fractional part of the mantissa, it would be 1110 and then just a whole bunch of zeros. Filled it up with zeros. Okay? So now you have to string everything together. Okay, so the final answer is going to be the 1, which is coming from the sign bit, the E, which is 1 followed by 7 zeros, 1, 2, 3, 4, 5, 6, 7, and then 100. That's the E component here. And then the rest is the fractional mantissa, which is just 1, 1, 1, 0, blah, 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 all zeros down here. Are we good so far? Are we done? Not quite. If you get to this point, you will get a lot of the points, but you won't get all of the points. Because the question clearly states that I want you to derive the hexadecimal representation of the bit pattern. I have the base 2 representation right now. But from base 2 to base 16, once again, it's pretty easy. It's just a table lookup process. If you're not comfortable with doing all that conversion in your head, bring that table with you, okay? Because there's no reason not to bring that table. So now we just group these things into groups of 4 from left to right, okay? So we have one group here. That's our 4. So 0x4. And then we have a group of 4 here, which is a 0. And then we have a group of 4 here, which is another 4. And then we have another 4 group of 4 bits here. It's 1110, which is an E in hexadecimal. And then the rest, they're all zeros. So you should give me 12 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's it. That's your answer. No, in this case, I do want you to count the zeros. Or you can do a bit shift operator, okay? You can just say that this is 0x404E, and then just use a left shift operator. And how many bits should I shift to the left? No. One digit in hexadecimal is 4 bits. Huh? Come on, you can do this. 12 times 4 is 48. Yep. So I would take both of these as correct answers. So if you don't trust yourself writing 12 zeros, you can say left shift by 48 bits instead. Are we good? Okay. So everything is being recorded. I will release this, as soon as the class is over, so you can review it if you are not quite sure, what all this stuff is about, because it has been a while. Yes.
Did you say when the exam was going to be?
Next Wednesday. Yep. So it'll be next Wednesday. Make sure you put it on your calendar. Yep.
Just going back to the problem, how did we get 3C again from 60 as the hexadecimal value?
Because there are 3/16 in 60, and this digit is telling me how many 16s we have. So after we take care of the 3/16s, which add up to 48, we have 12 left. So this is telling us how many ones we have. 12 is known as 12 times 1, but we have the digit to represent 12, and that turns out to be C in hexadecimal. Yep. I mean, if your calculator has base conversion capability, you can use that. I mean, I don't consider that cheating. So bring your scientific calculator with you, okay? Just in case you want to, do some quick calculation. Are we okay with question number 7? Yes? Okay. All right. So with this done, I am going to okay, let me click here. Nope, doesn't like that. All right, zoom out, go back here. So with that done, we're going to go to, this is where you find it too, okay? You already have access to the share drive. So go to the share drive, go to old exam 1, and the one that we just walked through is 1189-x1-00. Okay. Now we can go back to shared and then go to old exam 2, and I just put this up, so it's new to us. This is what we had in spring 2019. Okay, so one semester ago. So once again, I'm going to download this and reopen it in Zerno so I can mark it up. And we just say download. There we go. And open it in Zerno. Okay. There we go. Yeah, I'm keeping an eye on the volume. You guys cannot see it. It's just a little bit to the right-hand side because yesterday I ran out of battery. This typically will last me about 2 weeks, so that must be one day I forgot to turn it off. It drained the battery. But I am keeping an eye on it. So we go to zoom, page width, there we go. So I'm just going to go through this really fast. This is something you have seen already. So other than the time and the date and also the location, the rest is pretty much going to be the same. Okay, it's open book, open notes. Bring anything that is either handwritten or printed prior to the test. No electronics other than a scientific calculator, but you can use a TI-84, okay, which is practically a small little computer. But you can use that if you want to. It's individual assessment, just like the other exam. You're supposed to work on your own exam. Bring additional sheets of paper. If you think, especially if you needed that in the first exam, you might need that in the second exam too. Write legibly. Okay, same stuff as before. Make your answers as complete as possible. Blah 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 blah. All right. So most of the stuff is the same as the previous one, including the fact that there are this exam accounts for 20% of your final grade. So let's move on and talk about the questions in this particular test. So question number 1 is the implementation. Basically, how do you boil this down into assembly code for TTP, the toy processor that I have. Okay, so we talked about this already, and your current lab is kind of like this. Okay, even though it is simpler, it is still the same kind of process. So we look at this piece of C code, we assume all the registers, A, B, C, and D are registers already, and they're unsigned, okay? Because you can see the type of A, B, C, D is already given to you, which can be important if there are comparisons, with those particular registers. Okay, so you look at this, and let's figure out how to get this done, okay? So you can see that register C is not used in here. So that's kind of a clue that you can use register C to help you in the process. So you can go through the whole conversion process, based on what we talked about in the previous class. Okay, you can do it structurally, step by step. This one is not too bad. Okay, so the way I would do this, and you can do the same thing, is instead of doing it line by line, okay, from the first line to the last line, this is the way I do it. Okay, B equals to 0 is easy to do, so I'm just going to do it as an LDI. Oh, okay, LDI B0. Okay, that's an easy one. So the next thing I'm going to do, remember I like to work on the control structure from the outside in. So I'm going to go take care of the while loop first. So the way you take care of a while loop is that you need a while. Okay, now whether you want this one here or how you want to label your stuff is up to you. I don't really, you can label it any way you want. Okay, so if you prefer to use just your L0, L1, L2, L3, that's fine. Because especially in an exam, because the longer the name of the label, the longer it will take you to write it. Okay, so it's up to you. It's kind of, there's a trade-off. But we already know that at the end of the loop, we have a JMPI instruction going back to the beginning of the label. So I'm going to do it right away. Okay. We also know that there's an exit label so that we know, oh, when the loop is done, when the condition is false, this is where we go. So I'm going to put the label right here right away. Okay, so this is while one end as a label definition. If you make simple, like silly mistakes in the syntax, like forgetting the colon when you define the label, I'm not going to take points off, okay? Because this is an exam. I'm not going to nitpick little things. Go ahead.
With like where you put the one.
Huh?
You put while one begin and then while begin one.
While one begin. Yep.
Yeah, same thing.
Same thing. Yeah. So as long as it's pretty clear, what it is.
Yeah.
Yep. So yeah. So in this case, let me fix that.
I did the same mistake.
Hmm?
I did the exact same thing.
You did exactly the same thing? Okay, so this is supposed to be while one begin. Okay, so now we need to take care of the condition. The condition is as long as D is greater than 0, we continue the loop, right? Which means when D is 0, we get out. Does that make sense to you? Okay, so here's the question. In the case when D is an unsigned integer, being less than or equal to 0 means it is 0. There's no unsigned representation for anything that is actually less than 0. So you can just test for 0 if you want to. Okay? Now, it depends on how you want to do it. If you want to do it the standard way and not to put any attention into optimizing the code, we can do it the long way. So if you want to do it the long way, we will be looking for the case when D is less than or equal to 0, then we exit, right? So then you have to load register C with 0 first because you cannot compare something to a constant. And why can't we do that? Why can't we do a CMP D0? Okay, I'll put it here, but this is not good, okay? We cannot do this. Why can't we? Exactly, because CMP can only expect 2 registers as its operands. And why is that the case? I'll keep asking why until we we have a satisfactory answer. So why can't we, why do we require that both operands of CMP to be registers? Yes?
Is it kind of to do with the way the ALU is wired that it needs to be registers?
Exactly. It has to do with how the ALU is wired. It also has to do with the compare opcode. It only expects like 2 registers, okay? And so you cannot have, compare D with a 0, which is a literal constant, or we call it an immediate. Okay, so syntactically, it would make sense that, oh, we want to just compare, we want to subtract 0 from D, and we should be able to do it. But the answer is no, we cannot do that. Because one, there's the architectural limitation, the pathways between, what can feed into the input 1, input 2 of the ALU. So that's one restriction. And then the second restriction has to do with the ROM itself, okay? The ROM itself does not have any opcode corresponding to dealing with a subtraction that has an immediate. So combining both of those limitations, we just go like, nope, we cannot do this. Okay? So this is my not so subtle way of telling you, do not give me something like this. There will be points taken off. Is that okay? Is that fair? Okay? All right. So we have to load C with a 0, and then we do a compare. Okay, so now we do a CMP. And you have to be careful about the order, okay, because you want to find out whether you're subtracting C from D or whether you're subtracting D from C. So right now, we do want to subtract 0 from D, which is subtracting register C from register D. And we are not storing the result, by the way, okay? So after the compare, okay, I'm squeezing a little bit here because there are 2 things to do. So the first thing you want to do is if it is less than, so if it's unsigned comparison, it is JCI to while 1 end. And we also have to double check and say if it is equal to, we still want to get out.
It's JCI and not JI.
It is JC because D is unsigned. Okay? So are we doing okay so far with this code? Because all this is saying is if D is less than or equal to C, which is 0, let's get out. Seems to make sense because the original code says if D is greater than 0, we stay in the loop. Are we good with this so far? Okay.
Would you say that one more time about which one corresponds to JCI and JZI?
JCI says if less than, and JZI says if equal to. All right. So this doesn't leave me any room for the stuff that is inside the loop. It's okay. This is what I want you guys to do too, is you just need to find out where you want to insert the code and then do something like this to say that, okay, insert this block of code into that point. Okay? So this will help you greatly in order to write the code in a structured way, because otherwise you have to start from line 1 and you don't know how many lines you want to leave in between stuff. This gives you an easier way to kind of leave enough space to do it. All right, so now we're going into the inside of the loop. We have to do a bitwise AND between D and 1. Okay, so we kind of know what we need to do because we need to first get the constant of 1 into register C. Again, register C is not used for anything else, so it's okay to use it as a scratch register. Okay. The next one, we also know this is going to be a bitwise AND operation, so that's no big deal. The question is, do we want to specify DC or do we want to specify as CD? Now, if you specify DC, it's going to change register D. If you specify as CD, it's going to modify register C. Which one is correct? We want to modify register C, because if you look at the C code, it says, don't modify register D. Leave register D alone. We just want to look at the result, but we don't want to change register D. Now, if this is D ampersand equal to 1, then you want to specify AND DC. because ampersand equal to is what we call a compound assignment operator, which means it is operating, okay, doing the bitwise AND, but it's also assigning at the same point, at the same time. But this is not ampersand equal to, so it is just ampersand. We're not supposed to modify D, but it's okay to modify C, okay? Because after all, C is just a scratch register. So that's why in this case, we want to specify AND CD. And then after that, we want to do the branch, okay? So if you remember, in a conditional branch, you want to specify the condition to get out. So the expression of when the condition says if D ampersand 1, that means we want to get to the then statement if D ampersand 1 is non-zero, right? Which also means if it is 0, we want to get out. How can we tell whether the result of bitwise AND is 0 or not? J what I? JZI, very good. So we say JZI to a label. And I know it sounds really silly, but just to be consistent with what I said in class, this is the first conditional statement in the first while loop on the outside, and we are jumping to the end of that thing. You don't have to do it this way, because it is a long label, but doing it this way, I can look at the label and I can map it back into the source code. Okay. So we'll do it this way, and then we define the label. So the label is while 1 underscore if 1 and, okay, colon. All right, so what else do we need to do after the conditional statement? We have D equals D right shift by 1 and A right shift by 1, right? So what we need to do now is to reload register C with 1. I'll do that later, because I'm doing it structure-wise. So I'm going from the outermost control structure to the inner control structure, and then we'll deal with whatever is nested within the conditional statement. Okay? All right. So after I load a 1 into register C, the rest should be fairly simple. The right shift, you don't have an option. Okay? To do a right shift, you have to use the right shift mnemonic. Okay? D is the one that we are modifying, and C specifies the number of bits we're shifting. So RSH right shift, the number of bits being shifted is specified by C, which is 1. Okay, that's good. And register D is the register that is getting affected. So that's done. And then the next line says, A gets a left shift by 1. But we don't have a left shift operator. Okay, when I had this test in the semester, most people just say LSH because it seems to make sense. We have a right shift, we probably have a left shift. No, we do not have a left shift. So you might want to have that opcode table with you so that you know what instructions are available to you. Okay? Okay, so if we don't have a left shift operator, what are we going to do? Well, I think doubling something is the same thing as a left shift, but we don't have multiplication either. But doubling can also be done by adding a register to itself. Exactly. So the left shift operation becomes add AA. And that's it. That's the second level of code. So now we deal with the third level of code, which is what is inside the conditional statement. Equal to A. Well, it sounds complicated, but it's actually one of the easiest things you can do. What do? We add, no, not increment. Increment always increment by 1. So we're adding A to B, basically. So what opcode, what mnemonic do I use? Add. And what would be the order of the registers? BA, exactly. This is the reason why I choose the order of the operand in the instructions. The left-hand side is the one getting changed, just like in an assignment operation. Are we good? This is it. This is the full answer. You can use exactly the same representation, which means you focus on one level of control structure at a time. Just use something like this that clearly indicates that the insertion point is, and you can do this multiple level, and I can follow that. Yep.
Do you think it would run into lots of problems if I wanted to do it top to bottom?
You want to do it top to bottom, because the problem is, um, if you do it like you will have to you the start label while loop, and then you specify the code to jump out. Then you have to track that you have to remember to put an unconditional branch here, and also have a label to mark the end of the conditional statement. Okay? I found it difficult for myself to keep track of all that stuff, while I'm working on the inside of a loop. So I just do it this way, so I don't forget easily. But how you want to do it is up to you. You can try it. I mean, you can just practice and see which way works best for you. It's because that can vary from one person to another person. I think my short-term memory is like 2.5 items. Like the third item, there's a 50-50 chance I might remember that. Just like a quantum computer. It's all probabilistic. So are we good with question number 1? Yes?
So the add goes after the JCI, right?
The add is between the JZI and the while one underscore if one and the label. Yep. So if you want to be clear, you can just. Are we good so far? Yep.
What is about the JCI in the second control?
The JZI to which label?
JCI while one underscore if one.
This one here?
Yeah, if you go one above, what is that?
And CD. Yep. So are we okay so far? So I do think it might be helpful for you to use a pencil instead of a pen to answer the questions, because that gives you the ability to erase something, and then you don't have to like keep scratching stuff. Someone did in the first test. It's okay. I mean, I can still follow what is not scratched, and somebody they have to like circle the actual answer and write very explicitly, this is my final answer, point here, right? And then scratch that. Not final yet. So a pencil is fine. There's no. I know in many other classes, your professor wants you to use indelible ink. When you turn in answers like that, because they don't want people to have the opportunity to get the test back, change something, and then go back and ask for points. But since I scan everything first, it's not going to be an issue. All right, question number 2. Come on, question number 2. There we go. Oh, I like question number 2. So question number 2 is asking you to come up with patterns here, okay? And so let's read the question, which is kind of long, but we have to read this question. In many algorithms, bit 0 of a binary representation of a number is special. In other words, we want to know what is bit 0 of something. And we often have to test it. Furthermore, testing bit 0 is often followed by a conditional branch depending on whether the bit 0 is 0 or 1. In C code, this is what we want to do. We want to bitwise AND a particular register with 1, and if this is non-zero, we want to go to L1. Okay. Let's change bit 0 to bit 7. Okay. So we're going to change. It will be obvious why we have to make this modification. So this is going to be 7, and this is going to be 7. Okay. And that's also going to be 7. Okay, there we go. So bit 7 is, so this is not going to be 1. So what do we use instead of 1 to specify a number or a value where only bit 7 is a 1 and every other bit is a 0? It's going to be 1 followed by 7 zeros in binary. So what is it in base 10? What is 2 to the power of 7?
128.
128. Very good. Okay. So I'm marking up this question because bit 0 doesn't work. So we have to rely on, but this will work. Okay. So now we can continue to read. You can assume the opcode assembles in a way similar to JMP-IL1, where the first byte is the opcode and the second byte stores the value of the label L1. Okay. So that means, it's the opcode we are inventing. Okay. It does not yet exist. The opcode we are inventing is going to have the same kind of format as JMP-L1 or anything that has an immediate. Imagine that we have a new opcode with a mnemonic of TB7, test bit 7, and jump if it is a 1. Okay, so we'll change that to a 7 too. Okay. To do the same, it does not matter what the opcode is. In other words, the actual bit pattern of the opcode, we don't really care, what it is. But the microcode to implement this operation is important. So we want to figure out the microcode for this particular opcode. In the following table, specify components of the microcode to perform the same operation. In your microcode, use asterisk to indicate a particular field that does not matter and therefore can be any value. So anything that is like not care, it can be anything, just use an asterisk. For everything else, you have to specify the exact value that goes into that particular field. Okay? And let me just scroll down and see if there's anything else. Not much. Okay. Be sure to use this symbol correctly as it is a part of the score for this question. You may or may not need 3 size slices of microcode, but you will need at least 1. Okay, that's kind of obvious. The last microcode to reset microcode pointer is not needed in your answer. So you can just leave that one out and not worry about the 1 slice of microcode that says, okay, reset the microcode pointer back to 0, 0, 0. So you don't have to include that as one of the 3 here. Is that okay? So how do we answer this question? First thing is you pull out the diagram of the processor, which means it might be a good idea to jot down a note and say, bring TTP schematic. And you might want to look, you might want another one for the ALU and another one for the register bank. They may not be as important, but nonetheless still good to have. Okay. And in case you think you might need more than one because you want to mark up one and draw lines and annotate it for one particular answer, and you don't want to have to erase everything for another answer, you might want to bring like 2 or 3 pieces of paper, and each one has the schematic of the processor on it. Okay. All right. So how do we answer this question? What do you think? What would you do if this is what we need to do? And given the connectivity between components of the processor, how can we achieve this? If and only if bit 7 of a register, in this case, it is specifically register A, okay? If bit 7 of register A is a 1, we go to label L1. If not, we just continue with whatever is after that. Yes, go ahead. You would not need to do that. If you did that, that's actually, then you'll need 3 bytes to get this accomplished, because you will have to specify the 128 as a byte, next to the opcode. So I suppose you can do that, but you would be clobbering another register, which the C code did not. Okay, so we'll focus on the way to do this without clobbering another register. How do we do that? Yes?
Do we use like something like or and have a number that's like 128?
Mm-hmm.
Or like A with 128?
You're getting close. Now, the idea of using or and is correct. Okay? So what did you learn about and or in one of the labs that we have done already? One of them is hijacked, right? And the one that is not hijacked is useful for what? Setting flags. Setting flags based on a register, right? And which flags would it affect? Not all. Some flags are only used when we have addition or subtraction. So, to be more specific, okay, to be more specific, the carry flag, the sign flag, and the L flag are only affected by addition and subtraction. Okay? But that leaves two other flags, right? That leaves us the sign, no, I shouldn't say it's the sign flag. The carry flag, the L flag, and the overflow flag. Those three are affected by addition or subtraction only. But that leaves us with two other flags, the zero and the sign, right? So those two flags are affected by everything that goes through the ALU. What things would go through the ALU? Add, subtract, right shift, bitwise not, bitwise and bitwise or. I'm using that order because I think that is the correct order in the ALU. Yes? Yes. Which is also known as the sign bit. Oh, 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 okay. So the first slide is to specify an either and or operation with register A and itself. Okay? All right. So knowing that we want to feed register A from the register bank to both inputs of the ALU, and we want to specify an AND operation that does not store the value, the result, back into the ALU, into the register bank, how do we do that? You go like, right? Nope, doesn't have to be like that, okay? Assuming you have your processor schematic in front of you, along with the ALU, also schematic of the ALU also in front of you. Let's work out this table one by one, okay? It seems like it's going to be a hassle, but it's not. Okay, so we want to look at the PC enable, okay? Are we going to update the program counter when we just want to test whether a register has a particular bit set? The answer is no. Okay. So that means if this is a 0, okay, let me change back to a black color. That means mux can be whatever, okay? Because PC mux is what we specify to this is what we do. This is what we specify to influence how the program counter is getting updated. Since we are not updating the program counter, PC mux can be anything because it's not going to be it won't cause any problem. Okay, address mux. Are we driving the address port of RAM? Okay, are we using RAM at all? If I just want to test whether a register has the sign bit being on, do I need to access RAM? Yes or no? No. Okay. So that means, okay, so that means I go to RAM cell and say, no, we are not using RAM. Well, that will give us a whole bunch of asterisks automatically, right? Because if RAM is not being used, RAM load can be whatever. What else is related to RAM? Address mux is also related to RAM because address mux controls what is being used to drive the address port of RAM. If we're not using RAM, who cares, right? Okay. What else do we need to specify? Are we using the ALU? Okay, so that means ALU enable has to be a 1, okay? Now, if ALU enable is a 1, then you automatically have to answer the question that is right on top of it, is what ALU operation do you want to specify? It's either or an and, okay? Both will get the trick done, just pick one. So now we start up the logic sim, because I cannot remember, the number. Uh-oh. It doesn't like that because I specified too much stuff. There we go. All right, so here's logic sim. And we want to go into the ALU, which is here. Right click, do the view, and we can choose one of these two. Okay, pick one. If you choose AND, you have to specify a number of 4. If you choose OR, you have to specify a number of 5. So one or the other will work. Doesn't matter which one you choose. So now we go back to the table and just pick one. Okay, I'm just going to pick 4. Okay, all right. So what about the other bits? Yep, go ahead.
Why are those numbers specified for?
Because when you look at the multiplexer that is feeding into this thing here, so you look up this wire and say, okay, who's feeding into the AND gate? It is the output 4 of this demultiplexer, and this is being selected by operation select. So we need operation select to be 1, 0, 0 if you intend to use AND, and we need it to be 1, 0, 1 if you intend to use OR. Okay? All right. All right. So let's see what else we need to. What else is easy to answer? Okay. Are we updating any registers? No. So if we are not updating any registers, RIEN is going to be a 0 because that's register input for the register bank. Okay. So select is going to be asterisk. Because remember, if you don't care, you have to say asterisk instead of a specific value. What about RI mugs? So I'm not sure because I cannot remember the full architecture myself. So the tunnels are the same name as the names used in the table. So now we can look up, what was it again? RI mugs? Yeah. So RI mugs is this one here, and it can be anything. Because the multiplexer is turned off anyway, so you can choose whatever input because there will be no output whatsoever. Okay, so based on that, RI mux is also going to be an asterisk. All right, so now we get to the actually more important stuff, which is RO1 and RO0. So let's do RO0 first. Okay, we do want this to be enabled because we want to feed register output 0 to input 1 of the ALU. Okay, let me point out what I'm trying to do here. I'm trying to tie this wire all the way to here. Oh, that's pretty easy, right? Because I have to enable register output 1, which enables this particular multiplexer. And for that particular multiplexer, I will need a value of a select of what? A select of 1, okay? And that is known as RO0D mux. Okay, so RO0D mux has to be 1, RO0EN has to be 1. Okay, so I go back to the table, fill in those numbers. So we want this to be a 1, and we also want that to be a 1. So now we have to look at register output 1. Okay, so we switch back to here. So register output 1 is right here, and I want to route it to here. So it's a little bit more involved because I have to go through this demultiplexer first. So what should I use as register output 1 demux? If I want to connect this guy to this guy here, it'll be a 1 as a select. So I will need register output 1 demux to be a 1. Register output demux is a 1. Now I need to specify, I take that back. There's one that really should not be determined just yet. It's this one here. Okay. All right, so now I have just basically 2 left to deal with. Register output 1 select is basically specifying which register within the register bank do I want to present to register output 1 of the register bank. Register output 0 select is doing the same thing, but to register output 0 of the register bank. Which one what value should I put here? Look at the 0 in both cases, okay? So we put zeros in to both, okay, 1 here and 1 here. Instruction register enable is going to be a 0, okay, because we are not fetching. The only time you have that one being a 1 is when you fetch. Okay, so for the most part, what you do should not have instruction register enable turned on. So now we only have bit 24 and bit 25 left. Okay. So now we go to the ROM, and then we track down 24 and 25. So this is bit 25. Bit 25 is the one that resets the microcode pointer. Do we want to do that? Probably not. Okay. So we put a 0 there. It is not a not care, it has to be a 0. Okay. And bit 24 coming out of the ROM, okay, is this guy here. And that is how we choose, are we going to decode or are we just incrementing the microcode pointer? What do you think? What should this wire be if I just want to move on to the next slice? I just want to get on to the next one. It has to be a 1, because if it is a 0, it's going to reload the instruction register into the microcode pointer, which is the decode. Decode should only be done as the falling edge when the microcode pointer is 001. So it should be a 1 going into this multiplexer. So that should be a 1. Okay, so we put a 1 here. The first column is now done. So if you look at this column, okay, it is almost exactly the same thing as the opcode of AND AA. Almost. The only difference between this and AND AA is AND AA also updates register A, which is totally not needed. Are we good so far? What is the next one? The next one, now that we have register A tested, which means we have used register A to update the 2 flags, the 1 flag that I really need, which is the sign flag. I now need to look at the sign flag and say, if the sign flag is a 1, we are going to label L1. Do we already have an instruction that does that? We have JSI that is doing that already, right? So if you have this table decoded for the JSI microcode, you can copy the majority of it, okay? If not, well, we'll go ahead and figure it out. Okay, so the program counter is going to be updated, okay? One way or another, it is going to be updated because that's how we perform branching, okay? Or moving on to the next one. So if the program counter is updated, we also have to specify PC mux. So we go back to the schematic, and then we look up PC mux and find out, okay, what does it do? Here's PC mux right here. So PC mux is used to select the input into this particular multiplexer, which in return becomes PC mux. Okay, so if I want to pay attention to the sign flag, which is, let's see, bit 0 is C, bit 1 is Z, bit 2 is sign. Okay, so what should I specify as PC mux? Okay, let's see what, let's check out these wires, okay? So let's check out this particular wire and find out where it's going, okay? Where is it going? It's going to the register, the flag register, right? Bit 2 of the flag register is the sign flag. So how should I specify PC mux? 2. In other words, I am going to take input 2 right here to become the output to PC mux, because that is how I make decisions. Is that okay? All right? What if you say, but I totally forgot about the bit order of all the flags? Well, that's why you want to have your ALU schematic with you, because if you do have that with you, then you can see the ordering of the bits. Let me see if I was right. Bit 0 is carry, bit 1 is 0, and then bit 2 is in fact our sign bit. So I can double check, okay, and say that, okay, bit 2 is what we want. Okay, go back to Zerno, and then we specify 2 as PC mux. Well, every time you access RAM, okay, are we going to access RAM? Potentially. It's a conditional branch instruction. So with a conditional branch instruction, how do we specify where we are supposed to go? It is in RAM as the second byte of that instruction. The first byte is the opcode, which we don't care, but the second byte is the immediate, which is the label or where we're supposed to go. So the answer is yes, we do want to access RAM in this case. There's a chance that we will access RAM. Okay, so that means RAM select is going to be a 1. And since we're reading, RAM load is also going to be a 1. We're not going to update any registers, so I might as well just turn register input enable to a 0. And this is an asterisk, this is an asterisk. We are not using register output in either one. So we'll basically say we don't care which register we're selecting. The multiplexer, it can be important. I'll take a look later on. We're not using the ALU, so ALU enable is a 0, which also means whatever operation we want to specify can be whatever, because the ALU is not enabled. But now we want to look at address mux. Okay, go back here, and address mux. Oh, I have to go back to main circuit first. So address mux is the one that specifies how do we drive the address port of RAM. This is address mux itself. Okay. So do we want the program counter to drive the address port, or do we want something else to drive the address port? This is the same as a JSI instruction. So in the JSI instruction, it is the program counter that specifies where do we want to read RAM from. So that means we want to use input 1. So address mux needs to be a 1. Okay, so we put a 1 here. I just need to know whether we need to set register output 1 demux. Okay. Register output 1 demux is here. Okay, this is the wire that we are concerned about, and we want to know, okay, can we tell it to be anything, or does it have to be a specific value? So in this case, you can see the output of this, the multiplexer goes into here, but since we're already selecting the other one, this will not conflict with things that we want to do. And if it goes the other way, it goes into the ALU potentially, but we are not enabling the ALU either. So that means register output 1 demux can be a star, can be an asterisk, because it doesn't really matter how we specify that. So it's an asterisk here. And the register output 0 demux, okay, we double check that. Register output 0 demux is this wire, and it controls whether the output of the register bank is driving this wire, or this wire. Now this one is also not important because register output 0 enable is a 0 already. Okay, and let's make sure that is okay. We put a 0 here. So if that multiplexer is already turned off, it means it doesn't really matter how we select. Is that okay? And then register input, in the instruction register enable is a 0 because we are not decoding. We are not resetting back to location 0, 0. So bit 25 is going to be a 0. We just want to move on to the next slide, and that's why bit 24 of the ROM is also going to be a 1. And that is the answer to this particular question. Silence. It is a lot. But it is not something that I have not talked about.
But just barely though. Like I don't feel like we had enough experience with this processor to be able to walk through these well enough. That is
But I did mention the way to study for this class is what again? To use the toy processor, Control T, freeze the frame, understand how the components are connected because of the bits in the ROM. I did mention that. And I got it recorded multiple times. Yes.
So ROM 24.
Yep.
If that's enabled, it moves to the next slice of microcode as it happens?
So let's check it. Okay, so if you look at bit 24 of ROM, which is this particular wire here, It is used to determine, are we incrementing because of this input being selected, or are we decoding because the other input is selected? Is that okay?
So if we increment, it means we're going to the next address in that location.
Yes, we're going to the next location,
So
which in this case would be the one that has bit 25 being a 1, so that we can reset back to location 000, because we're all done.
So we need a third instruction that has the 25 set.
Correct. We'll need a third slice, but since the question said you do not have to specify
That was
the one that resets microcode pointer, so that's why I'm not going to put it into the table.
does every instruction have
Yes.
basically have
So every instruction has that slice to reset the microcode pointer, except for the halt instruction. Yeah, because the halt instruction just wants to keep decoding, so that one basically does not need to reset back to location 0.
So what would be sitting in the instruction register right now that would be the original opcode that says to perform the.
So whatever opcode we are currently executing in microcode will be stored in instruction register.
Okay. So that was the address of the first instruction that started off this whole process, the check in bit 7 was.
Say that one more time.
It's the address in ROM of, or the non-multiplex address in ROM of the first slice microcode that implements this.
So location 000 in ROM on the rising edge is updating the instruction register, and that's what we call the fetch operation.
That was what we put in RAM.
That's where we read from RAM and copy the content of one location of RAM into the instruction register. That's fetch. Because we are trying to read the opcode that we want to execute. On the falling edge, when the microcode is 001, that's when we decode. That means we take the output of the instruction register, combine it with the least significant 4 bits of 0, and turn that into our microcode pointer. That is decode, because once we have done that step, the microcode pointer will now point to the correct slice in the ROM that implements the opcode that is still being stored in the instruction register. Okay? So what does it mean? So how do we study for this kind of question? So go through the instructions, okay? There are groups of instructions. In other words, you don't have to do every single possible instruction. So with everything that affects the arithmetics, okay, choose one, okay? And, single clock through the whole thing, look at the bits of the ROM and understand how the components are connected as a result of the microcode, okay? I would choose one that is a conditional branch, okay? Doesn't matter which one. Choose one of the 4 or 5, okay? JCL, JCI, JZI, JOI, JSI, and then JLI, okay? Pick one of those 5, okay? Because the only difference between the 5 is which of the input of that big multiplexer is choosing as the input. That's the only thing that it changes, okay? But you do want to understand how it performs a conditional branch. What if that flag is a 1? What if that flag is a 0? How does it know, oh, we just want to increment in this case, but in the other case, I want to use whatever the program counter is pointing to update the program counter itself. So that is what you need to do, okay? I have gone through this exercise for a few instructions already. And you will need to do the rest, okay? You'll look at the other instructions, and I think we have covered basically all of them, except for maybe load and store. So I would say look at load and look at store, okay? Pick one particular combination, okay? And single clock it, okay? Single edge it until you get to the microcode corresponding to that specific opcode, and then go through the same exercise, okay? Look at every single component, figure out whether it's enabled or disabled. If it is enabled, how does it connect to other components? Okay, the more you do this, the faster you can go through this process. Is that okay? That is how I think you can study for this test. If you do have questions, like, I'm looking at one particular instance, okay? I can see what the bits are coming from ROM. I can see what components are connected, but I don't quite see, how it is getting what it is supposed to be done. I can answer those questions. And that is what next Monday can be useful. is for you guys to go through this process, okay? Go through most, if not all, of the groups of instructions. If you find one that you go like, I'm not quite getting how this is done, then bring that question to Monday, and I'll be more than happy to go through this process and explain how instructions work. Yes?
It's a holiday.
Monday's a holiday. Darn. Somehow I don't keep track of holidays. Okay, so I don't want you guys to have a test before we have another class. So we'll move the exam to the Monday after next. Okay? Well, that gives me more time to think about what questions I want to ask too. So I'm not really sure. I think it's a wash. I think it's a wash, but if you want to think it's good, yeah, sure, go ahead. Optimism, yes. But so that means, if you have any questions after you study, the pathways and whatnot, you'll bring those questions next Wednesday, and we'll finish this on next Wednesday. Yep.
Final answer one more time.
Huh?
The final answer for this.
Oh, sure. It's all getting recorded anyway, so you don't trust my recorder.
I don't trust this. You might get some.
What time are your Tuesday classes?
So the Tuesday class is supposed to have the exam next Thursday, but since I'm moving this class, I'm intending to move that class too, just so that the two classes won't have like a whole weekend in between.
Okay. What time? So I'm gonna have to leave on Tuesday night for my grandmother's funeral
Okay.
service. That Tuesday, what time is